Hello, myself G. Sai Vishal and I am from CSE department. My subject is LAC. My topic is on Rolle's theorem. History. A version in history, a Rolle's theorem states that a version of the theorem was first stated by the Indian astronomer Bhaskara in 12th century. The Rolle's theorem was first stated by the Indian astronomer Bhaskara in 12th century and it later known in all forms by Michael Rolle in 1691, which uses the methods of different calculus. First, it was uh, stated by the Indian astronomer Bhaskara, and later it was known in all forms by Michael Rolle in 1691. Proof. The Rolle's theorem states that suppose f is a function which is in continuous on the closed interval a comma b and differentiable in an open interval a comma b. Suppose in addition that f of a equal to 0 and f of b equal to 0, then a point c is lying strictly between a and b such that f dash of c equal to 0. Here f is a function which is in continuous in an closed interval a comma b and differentiable on open interval a comma b. Suppose f of a equal to 0 and f of b equal to 0, then there in between these two point c lying strictly between these two, then f dash of c equal to 0. A continuous function on a closed interval attains a maximum and a minimum on the interval. If at a point where a differentiable function has a max or a min, that minimum, that derivative is 0. The differentiable function which has maximum or minimum value, the derivative is 0. The plan of the proof is to break the situation up into three cases. The cases are: first statement states that f is not positive or negative on the interval a comma b. F is positive somewhere on the interval a comma b. F is negative somewhere on the interval a comma b. Case 1. F is not positive or negative on the interval a comma b. If the function f is not positive or negative on the interval a comma b, then f must be 0 everywhere on the interval. F should be neither positive nor negative. If not both, it should be 0 in every cases, that is f equal to 0, and in particular f is constant, the derivative of a constant function is 0. Then if then the function is 0, then the derivative of the constant function is also 0. So f dash of c equal to 0 for all c between a and b. Thus the conclusion of Rolle's theorem holds in this case. Therefore first case is satisfied. Then second case, f is positive somewhere on the interval a comma b. Suppose that f is positive somewhere on the interval a comma b. A continuous function of the closed interval takes on a maximum value somewhere on the interval. Suppose that f attains the maximum at x equal to c. Since we know if f is positive somewhere on the interval, the max f of c must be positive. If the function f is positive somewhere on the interval, then the maximum value f dash of c must be also positive. Since f dash of a equal to 0 and f of a equal to 0 and f of b equal to 0, c can't be either a or b. Therefore a less than c less than b. In particular, f is differentiable at c, but at a point where a differentiable function attains a max, the derivative is 0. Thus f dash of c equal to 0, and Rolle's theorem holds in this case. If the f dash of c equal to not equal to 0, then the Rolle theorem not satisfied. Case 3. f is negative somewhere on the interval a comma b. This case is similar to case 2 which we concluded in the past. Suppose the f is negative somewhere on the interval a comma b, a continuous function on a closed interval takes on a minimum value somewhere on the interval. Suppose that f attains its minimum value at x equal to c. Since I know f is negative somewhere on the interval, the minimum f of c must be negative. The function if is negative, then the value of f dash of c also negative. Since f of a equal to 0 and f of b equal to 0, c can't be either a or b. Therefore a less than c less than b. In particular, f is differentiable at c, but at a point where a differentiable function attains a minimum, the derivative is 0. Thus f dash of c equal to 0, and Rolle's theorem holds in cases 3. Since these three cases cover all the possibilities, the proof of Rolle's theorem is complete. Even though in these three cases any one case is not applicable or not satisfied, then the Rolle's theorem doesn't satisfy. First example, a semicircle of radius r. For a radius r is greater than 0, consider the function f of x equal to square root of x square minus x square, where x belongs to the interval of minus r comma r. Its graph is the upper semicircle centered at the origin shown below. This function is continuous on closed interval minus r comma r and differentiable in the open interval r comma r minus r comma r, but not differentiable at the endpoints minus r and r. Since f of minus r equal to f of r, Rolle's theorem applies, and indeed there is a single point where the derivative of f is 0, a semicircle of radius r. Second example, if differentiability fails at a single inner point of the interval, the standard version of Rolle's theorem can also fail. If a single inner point of the interval fails, then the standard version of Rolle's theorem also can be failed. For example, for some real a greater than 0, consider the absolute value function f of x equal to mod x module x. X belongs to the interval minus a comma a. Then f of minus a equal to f of a, but there is no c between minus a and a, for which the derivative is 0. This is because that function, although continuous, is not differentiable at x equal to 0. In this above function, the function is continuous but not differentiable at x equal to 0. Note that the derivative of f changes its sign at x equal to 0, but without attaining the value 0. The graph shown below, the graph of absolute value function, we can see that y equal to mod x. Third example, consider the function f on minus 2 comma 2 given by f of x equal to under root of 1 minus x minus whole square for x belongs to 0 comma 2, and minus under root of 1 minus x plus whole square for x belongs to minus 2 comma 0. Its graph consists of two semicircles, but put together is a smooth way at the origin. The function is odd and satisfies f of 2 equal to 0 equal to f of minus 2 also 0. It has infinite slope at the origin and is therefore not considered differentiable at x equal to 0. However, the assertion of Rolle's theorem is still true. There is even more than one point on minus 2 comma 2 where the derivative is 0. Function consisting of two semicircles joined smoothly at the origin. We can know about the still later information about the Rolle's theorem. Sources are proofs from, and we can see the websites which we can gather information about Rolle's theorem. Thank you.